In this video, we continue with Chapter 6, Section 6.5, all about applications of linear transformations. And our learning objective for this video is to use a linear transformation to rotate a figure in R3. So here we are going to see the ways that you can rotate a 3D point XYZ. So if you want to rotate the point XYZ counterclockwise, we always work counterclockwise here in math, about the z-axis like we see over here in this image, through an angle that we'll say is theta. So here's angle theta down here. Then the coordinates related to the rotated point, we're going to call those x prime, y prime, and z prime. And here's our formula to get them. So you're going to rotate using the matrix cosine theta, negative sine theta in the first row with a 0 for the z because z is unchanged. And then you're going to have sine theta, cosine theta, 0 in the second row, the 0 where the z goes because z is unchanged. And then your third row is going to be 0, 0, 1 because the z axis remains unchanged. And that simplifies when we multiply it by xyz to this formula here, x cosine theta minus y sine theta in the first row, and x sine theta plus y cosine theta in the second row, and z in the third row because z remains unchanged. We're just rotating about the z-axis. So our rotation goes counterclockwise, and you can visually see it here. So there's three ways we could rotate in R3. We could rotate about the x-axis. So then in our matrix, the cosine, negative sine theta now shifts to the second row, and the sine theta, cosine theta shifts to the third row. And notice, since the x-axis remains unchanged, we have 1, 0, 0 in the first column and the first row here. And then you'll see that when we rotate about the y-axis, we maintain the 1, 0, 0, or the 0, 1, 0 in the second row and second column. And then we've got our cosine and negative sine in entry row 1, column 1, and row 1, row 3, column 1, and our sine theta and cosine theta in row 1, column 3, and row 3, column 3. So you can see how those move around here. And then for rotation of the z-axis, that's the matrix we saw with cosine theta and negative sine theta 0 in the first row, sine theta, cosine theta 0 in the second row, and 0, 0, 1 in the third row, because we're preserving z, we're rotating about z. So you can see kind of visually those ones end up in the places where we've got x, y, and z that we're rotating about. So here's a visual of how rotation of the x-axis looks. Here's a visual of how rotation of the y-axis looks. And then we saw rotation of the z-axis. In all of our rotations, we go counterclockwise. That's our default mathematically. And then there's what's known as the right-hand rule that you've probably seen in physics class about how we orient our rotation. So if you go counterclockwise with your right hand, your thumb will point in the direction of the axis that we're rotating about. In physics, we think about this as the cross product in that direction that you see here. So in mathematics and physics, the right-hand rule is a common mnemonic for understanding the orientation of the axes in 3 dimensions. Most of the various left and right-hand rules arise from the fact that the 3 axes of 3-dimensional space have 2 possible orientations. So make sure you're using the right hand when you do this. If you use your left hand, you get opposite results. And then you can always look back at our diagrams to check. You don't have to use the right-hand rule to figure out which way things go. But if you rotate with your right hand, then your thumb points in the direction of the axes we're rotating around. And here's another image of it. So this remark says, to illustrate the right-hand rule, imagine the thumb of your right hand pointing in the positive direction of an axis. The cup fingers will point in the direction of the counterclockwise rotation. The figure below shows counterclockwise rotation of the z-axis. So let's take a look at some examples. We're going to start with this original tetrahedron and then look at the pictures of the rotation and just explain how it was rotated. Once we know the degrees or angle theta and radians that our tetrahedron is rotated by, Then you get to come back to these matrices and set up your rotation matrix and act on all your points with this rotation matrix. And so after we look at some examples of figuring out rotation angles, then we'll look at an example of actually applying a matrix. So in this first picture here, here's our tetrahedron, and it got rotated about the y-axis. It's kind of like somebody knocked it over on its side is how I usually see it. So see how it's like it came kind of down this way? And so it got rotated 180 degrees about the y-axis. And then here in our second example, it got rotated in the z direction. We rotated this way 180 degrees. So that's a 180 degree rotation about the z-axis. And then we want to determine also for these diagrams. So this one is just a 90 degree rotation about the z-axis. If you look back at our original diagram, you can see, oh yeah, it just moved about 90 degrees around the z-axis. And then here's what our tetrahedron would look like if we rotated it 180 degrees about the x-axis. So this one went over this way. So you can kind of think about it rotating with the origin point fixed, kind of spinning around 3D. So let's take a look about how we find the matrix that produces rotations like this. So we're going to find the matrix for a rotation 60 degrees about the x-axis. So this is a matrix where we've got 1 in the first row, first column, and then zeros in the other places in those columns and rows. And then in our cosine theta, negative sine theta, and sine theta, cosine theta positions here, we put in 60 degrees. And then using what you know about the unit circle, you can just replace those with the values. And if you don't want to say 60s, you can say it in radians, pi over 3. Your choice whether you use degrees or radians. Our textbook does degrees by default, but radians are obviously equivalent. And so we get those values 1/2 and negative root 3 over 2 for the negative sine of 60 degrees. And then in the third row, we've got the root 3 over 2.5 for the sine of 60 degrees, or maybe more familiar to use sine of pi over 3. And the cosine of 60 is 1/2, or what you think of as cosine of pi over 3. All right, now we want to see how does the matrix look if we're rotating 60 degrees about the y-axis. So we've got 1, 0, 0. That's just a 0. Oh, I think I pasted in the wrong value here. Hang on, I'm going to go back and fix this. And looks like I put in the wrong paste here. So hang on. Okay, so for 60 degree rotation at the y-axis, I pasted in the wrong matrix. So let's take a look at what the right matrix looks like. So for rotation about the y-axis, we're going to have cosine 60 here in the first entry. Then we have a 0. And we're going to have sine 60 in the third entry of the first row. Those are degrees. And then we're going to have 0, 1, 0 because we're rotating about the y-axis. And then we're going to have negative sine 60 degrees, 0, and cosine of 60 degrees. Okay, so then if we want to rewrite that in terms of what we know about the unit circle, cosine of 60 degrees is 1/2. So we've got 1/2, 0, and then sine of 60 is the root 3 over 2. Then in the second row, we've got 0, 1, 0, because we're rotating about the y-axis. And then negative sine of 60 is going to be negative root 3 over 2. Then we've got a 0, because we're rotating about the y-axis. And then we've got cosine of 60 degrees, which is 1/2. So you could write your matrices either in terms of the cosine and sines, or you can go ahead and use the unit circle to convert those. So we see to find matrices for rotations, it's fairly straightforward. You'll use these matrices of rotation that are given to us here in section 6.5.